Hey everybody, I hope you're enjoying your second snow day. I wanted to give you a little bit of the lesson that we would have learned on the double day. This is really only about half of it. It comes from section 2.6 in your book, so we'll just call this 2.6a, and we're talking about rational functions. Of course, please feel free to pause the video if you need to while I'm explaining things so that you can write it down, or rewind if you need to listen to something again or you're confused. All right, here we go. We have 3 objectives for this particular video. The first objective is to find the domain of a rational function. The second is to determine the end behavior of a rational function. And the third objective is to find vertical and horizontal asymptotes of a rational function. So you can see a trend here. Everything we're going to be working with today is a rational function. So I suppose we should start talking about what a rational function is. This may seem obvious, but a rational function is a quotient of polynomial functions. So usually it is in the format of this. Let's say that you have f of x, and that's going to equal some function on the top that we're going to call n of x, and then another function, and then the bottom, which we will call d of x, for numerator and denominator functions. This is where n of x and d of x are polynomials, so they have to be polynomials, and d of x is not the zero function. So you've done some work with rational functions in Algebra 2, and we're going to go a little bit farther with it this year. Let's start out by finding the domain of a rational function. Example 1, let's find the domain and discuss the behavior of f near any excluded values. All right, let's just maybe start with an easy one. What if we have f of x equals 1 over x? We know that the domain of really any function starts off being all real numbers, and then we have to figure out where it's undefined, basically. So if we looked at this one, we would say, okay, this one has a domain of all real numbers, x, such that x does not equal 0. If x equaled 0, then this would be undefined, so that would be a problem. If you graphed this on a graphing calculator or something, you would see it looks like this. You also know this is a parent function that you're used to, so it looks kind of like that. It actually has an asymptote here and here. Let's talk about the behavior a little bit. So what's happening as the graph is getting closer to 0, like closer to x being 0? What's happening to that? We actually need to look at it from both directions. What's happening to the function as it approaches x equals 0 from the left side, and what happens as it approaches from the right side? I'm going to point at what's happening with my lightsaber. As I approach 0 from the left side, the function is actually going to negative infinity. And as I approach 0 from the right side, my function is actually going to positive infinity. That's something that we're going to talk about more in just a few minutes as far as like how to write that with proper notation, but I wanted to go ahead and point it out right now. Let's do one more example with finding domain. If I take a look at this, I know again that the domain is all real numbers except where it's undefined. So I'm concerned with the denominator. If the denominator equals 0, then we are going to have a problem. So you might be able to do this in your head, but I'm just going to write it off to the side here. Where does 3x plus 2 equal 0? I would need to subtract 2 from both sides, and then I would need to divide by 3. So the denominator equals 0 when x equals negative 2/3. That's going to be our excluded value. The domain should be all real numbers such that x does not equal negative 2/3. If we take a look at the graph, honestly, I just graphed this in a calculator just to kind of get a feel for what was going on. The graph looks kind of like this. This is not great, but it's something like this, where this value right here is about negative 2/3. Okay, that is the issue here. That's what we're talking about. So again, if I'm describing the behavior as it's approaching the excluded value, I see as my function here approaches from the right, as it approaches negative 2/3 from the right, this time my function is going to negative infinity. As the function approaches negative 2/3 from the left side, my function value is approaching positive infinity. Let's start using some proper notation now to actually discuss the end behavior of these functions. We are going to use a similar notation as before, so we would say something like, as x approaches infinity, ... As x approaches negative infinity, ... But now we're not only considering infinity and negative infinity, we also need to consider those excluded values. So, for the first one, we actually need to look at as x approaches 0. But then we also have to add direction to this because it approaches 0 from two different ways and it does two different things. So you're going to see a little plus sign. That means as it approaches 0 from the right. And you might see a little minus sign, and this means as it approaches 0 from the left. Let's talk specifically about that first function. F of x equals 1 over x. The graph looked like our normal parent function for a rational function, and it's kind of like this, where the asymptotes were at y equals 0 and x equals 0. When we're talking about end behavior, we're concerned with what's happening to the y values as the x value is approaching something. So let's just start off by talking about the left side. So we're only going to be talking about the left side of the graph. Here, this side. That didn't turn out the way I thought it would. Oh well. So we're talking about this part of the graph. As x approaches negative infinity, what's happening to my y? So x is going this way. It's approaching negative infinity. My y value is actually approaching 0. It's getting closer and closer to 0, but it's never touching it. So I'm going to say as x approaches negative infinity, f of x approaches 0. Now I also, on the left side here, I need to consider what happens as x is approaching 0. So again, when I'm saying that, I'm saying the x value is approaching 0. That's the y-axis. So as x approaches 0 from the left side, that's what the little minus sign means, f of x is approaching negative infinity. It's going down. Now let's focus on the upper part of the graph. Here. Again, there's two things that are happening. As x approaches positive infinity, my y value again is actually approaching 0. So I'm going to say f of x approaches 0. As x approaches 0 from the right side, that's the little plus sign, and that's what's happening right here. As x approaches 0 from the right side, my f of x approaches positive infinity. these four little phrases, if you will, explain exactly what's going on with this graph's end behavior. Instead of having two ends, this graph kind of has four ends. So that's why we have to have four different little phrases. Let's try it out with the one that was for part B. I've jumped a little ahead of myself in giving you this example because we haven't talked yet about how to find these asymptotes. That's the next thing we're going to do. So right now, I need you to trust me that this asymptote is at x equals negative 2/3. We clearly figured that out already because that was the excluded value in the domain. This asymptote is at y equals 4/3. I have not told you how to find that yet, but you might be able to look at the equation and figure it out for yourself before we actually do that part of the lesson. So knowing those two values, let's go ahead and write what the end behavior of this function is. We're going to start off with as x approaches negative infinity. And I'm going to use my lightsaber again because I can, except this time I'm going to use green. Okay, as x approaches negative infinity, what is the function doing? Well, it looks like it's approaching this line right here, which I just told you is 4/3. So as x approaches negative infinity, my function value is approaching 4/3. If I'm still talking about the left side of the graph, I also have as x approaches negative 2/3 from the left. So I have to put a little minus sign to indicate that I'm talking about the left side. So again, as I approach this up and down line right here is negative 2/3. So as x approaches negative 2/3, my function shoots up. It goes to positive infinity. Now I need to try the same thing for the right side of the graph, and I'll write it on the right side of the graph. This time we have as x goes to positive infinity. It's going, it's going, it's going. And again, it's approaching that green line, which is 4/3. It being f of x. F of x approaches 4/3. And then the last one is as x is approaching negative 2/3 from the right. So I have to put a little plus sign there. On the right side of the graph, as x approaches negative 2/3, the function shoots downward, which means f of x approaches negative infinity. Really sorry for the horrendous handwriting on this. Decided to use a new app this time, and I'm just getting used to it. But there you go. That's end behavior. Now we need to talk about finding asymptotes. This is the last objective of this particular video. Finding vertical asymptotes is something that you guys already know how to do because that is essentially where the function is undefined. So we've talked about this already. It's not a big deal. Basically, to find the vertical asymptote, you need to figure out where the denominator equals 0. Now, I will say the one caveat to this is if there are any common factors. So really, before you even try to find an asymptote, you need to make sure that n of x and d of x, the numerator and the denominator, have no common factors. Hypothetically, let's suppose that you have some kind of polynomial and you factor it because you're really awesome and you know how to factor. Let's suppose that you factored it and this is what you got. Well, right away you notice that this has a common factor. So these are going to go away. But you have to be careful because -1 still is not in the domain. Like now you have a more simplified function to graph and to look at, but you still need to take into consideration this value. This x cannot be -1. That does not make a vertical asymptote. What that does is it creates a hole at x equals -1. So you might have talked about this in Algebra 2, but this is just a reminder. Factor everything first. If you have two factors cross off, that creates a hole. Anything that doesn't cross off is going to create a vertical asymptote. So here, now that I have this simplified, I can see that 2 is going to be a problem. So x cannot be 2, otherwise we have an issue. And this is your vertical asymptote. So I'm going to say vertical asymptote at x equals 2. It's just going to be a straight up and down line at x equals 2. So finding the vertical asymptote is something that's relatively easy. You're just finding where the denominator equals 0 after you cross off the common factors. To find the horizontal asymptote, there's kind of some special rules, and it all depends on the degree of the polynomials. The graph of a rational function is going to have one or no horizontal asymptotes, depending on the degree of the numerator and denominator. I'm going to use lowercase n for the degree of the numerator and a lowercase d for the degree of the denominator. So notice I said that it has one or none. It's not ever going to have multiple horizontal asymptotes. It actually is possible to have multiple vertical asymptotes, but not horizontal. There's 3 rules, and it all depends on these degrees. So the first one is when the degree of the denominator is greater than the degree of the numerator. Your horizontal asymptote, I'm just going to abbreviate with HA, okay? When the degree of the denominator is greater than the degree of the numerator, the horizontal asymptote is going to happen at y equals 0. I want us to think about why this makes sense. So just a little example under here. Let's suppose that we have 3x divided by 4x to the third, 3x plus 1 divided by 4x to the third plus x. As this is written, the denominator has the greater degree, right? The degree of the denominator is 3 and the degree of the numerator is 1. Well, think about what happens if you plug in infinity or negative infinity. I know this is weird. I know you can't plug in infinity. Think about a really, really big number. If I plug a really, really big number into these x's, the denominator is going to get huge. And if you think about a fraction, if a fraction has a really huge denominator, that's actually close to 0. So that's why when the degree of the denominator is greater than the degree of the numerator, the horizontal asymptote is always y equals 0. Always. Because as you go to infinity, the y is going to get closer and closer to 0 because a fraction is actually getting tinier and tinier because the denominator is getting huge. It's probably way more information than you needed. The important part is that when d is greater than n, horizontal asymptote is y equals 0. Well, when the numerator degree is greater than the denominator degree, there is actually no horizontal asymptote. Okay? So an example of this would be something like 4x squared over x plus 1. This clearly is going to have a vertical asymptote because of the x, the -1 in the denominator. That'll have a vertical asymptote, but it's not going to have a horizontal asymptote. It's actually because of a similar reason. If you imagine hypothetically plugging infinity into these, the numerator is going to get a lot huger than the denominator faster. And so actually that causes the whole function to go towards infinity. It doesn't ever level out. It doesn't get stuck anywhere. It just goes to infinity. So that means there's no horizontal asymptote when the numerator has a higher degree than the denominator. And then lastly, when the degree of the numerator equals the degree of the denominator, this is the weird part, it's going to be the ratio of the leading coefficients. Okay, I'm going to say that again. When the degree of the numerator equals the degree of the denominator, the ratio of the coefficients is the horizontal asymptote. So you would have y equals an over bd, I suppose. It's whatever the first number is on the leading coefficient. I mean, it is a leading coefficient. So an example of this would actually be the problem that we did in the beginning. And I'm writing it off to the side here, kind of small, but it was the one that said 4x over 3x plus 2. Remember how I told you that the horizontal asymptote was going to be 4 over 3? And that was because those are the leading coefficients. They have the same degree, the numerator and the denominator do. So 4/3 is what you're left with. Again, if you imagine plugging infinity in, I know it's really weird. It's not possible, but you just kind of have to imagine. This little 2 over here is kind of negligible in the face of infinity. So if you plug infinity into the x's, it's kind of like the infinities divide out and you get 4/3. I know that's not really super mathematically correct, but I think it kind of gives you the idea of why it's 4/3. It approaches 4/3. Let's do some examples of this before we end. We are going to find all vertical asymptotes and horizontal asymptotes for each function below. Let's start with A. F of x equals 3x squared, all divided by 4x squared minus 1. Well, maybe the horizontal asymptote is actually easier because really you're just looking at the degrees. Do you notice how they're both squared? They both have a degree of 2. And so that means that my horizontal asymptote is going to be just the ratio of the coefficients. Right there. Now, horizontal asymptote is actually a y equals function. Because y equals would be a horizontal line. Y equals 3/4. There's the horizontal asymptote. To find the vertical asymptote, I need to set the denominator equal to 0. And for this one, I'm going to need a factor in order to solve it. This is actually the difference of two squares. I'm going to have 2x plus 1 and 2x minus 1. If I solve these, I end up getting x equals 1/2 and x equaling -1/2 and x equaling 1/2. Those are my vertical asymptotes. Let's do another one. F of x equals 7x cubed divided by x plus 8. You're probably not super familiar with the horizontal asymptote rules yet, so you will probably need to look back at your notes and see what matches this situation. Clearly, this is not the same as part A because that one had where the degrees were matching, and so you did leading coefficients. This time, the degree of the numerator is higher. So go ahead right now and look back at your notes and see what happens with the horizontal asymptote if the degree of the numerator is higher. Or you can kind of just think about what happens when you plug infinity in. What's it going to do? Did you check? Okay, hopefully you found out that this one has none. This one does not have a horizontal asymptote. It's going to actually go up to infinity. What about the vertical asymptote? What is going to cause the denominator to be equal to 0? That's going to be -8. So no horizontal asymptote and then one vertical asymptote where x equals -8. Let's do 2 more. This time let's let f of x equal x squared plus x minus 2, all divided by x squared minus x minus 6. Okay, I'm going to start with the horizontal asymptote again. Do you notice that we actually have the same degree once again? So same degree means that the horizontal asymptote is the ratio of the leading coefficients. I know there's not numbers in front of this, but technically they're ones. So y equals 1 is my horizontal asymptote. To find my vertical asymptote, I know that I normally just set the denominator equal to 0, but don't forget, part of the rule with the vertical asymptotes was that at that point there's no common factors. So it looks like we can factor the numerator and the denominator. Let's factor the numerator first. I need two numbers that multiply to -2 but add to 1. So that's going to be -1 and a +2. And then let's also factor the denominator. Two numbers that multiply to -6 but add to -1. Be careful. -3 and a +2, it looks like. Okay, so this is why this was so important for us to do. This is actually going to have a hole. Where's the hole going to be? If you thought -2, you were correct. There's going to be a hole at x equals -2. So now I need to look at the simplified version to figure out where my vertical asymptote is going to be. Vertical asymptote is going to be at x equals 3. That's going to be the problem. All right, so we have just one vertical asymptote, one horizontal asymptote, and then one hole. Let's do one last problem. This time, let's suppose that f of x equals 5x squared over 2x cubed minus 1. Once again, you're probably going to need to review your horizontal asymptote rules. I can see that the denominator has a higher degree than the numerator. Go ahead and look back at your notes, please, and see what that means. If you forget the rules, you can always think about plugging in infinity. If you could see me, I would be doing air quotes right now. Plugging in infinity into the x. If I do that, the denominator is actually going to get bigger faster. And as the denominator gets bigger, that means the function is actually approaching 0. So our horizontal asymptote is where y equals 0. I can't factor the numerator. It doesn't really look like I can factor the denominator. This is cubed. This is a little different, and there's not multiple x's either, so that's helpful. I'm just going to solve this kind of old school. Let's add 1, divide by 2. We're going to need to do the cube root on both sides. So technically we have that x is the cube root of 1/2. If I want to be really mathematically proper, I should rationalize this, I suppose. But since it's a cube root, I cannot multiply it only one time. I actually have to multiply it twice. This is the only way I can get rid of a cubed root. I need to have it multiplied 3 times. So I'm going to end up with the cube root of 4 on the top and then a 2 on the bottom. X equaling this is actually my vertical asymptote. The homework for this section is on page 177, and it's numbers 7 through 15, odd. That's actually not very many problems. That's only 5 problems, and I really hope you do them so that you can practice this. You do need to be able to find asymptotes and domain and describe end behavior by the time we return to school, because when we return to school we will be sketching these graphs, and in order to sketch these graphs you have to be able to find these things. And just to prove to you that Zeke is not always going to be scared of snow, hopefully, here he is, ever so slightly happier about the snow. He was happy as long as he was holding our hand. So I hope that you guys have a lovely day, and I will see you soon, hopefully. Stay warm.